Okay, so hi everybody, welcome back. What we're going to be doing today is a continuation of our chapter 20 lecture on entropy and the second law of thermodynamics. What we talked about last time was heat engines. So the basic picture of what's going on inside of a heat engine is you have an ideal gas and it undergoes a cycle. So it undergoes a bunch of different processes, but it always comes back to where it started, and then the cycle repeats. So that's how you can keep having the engine do work over and over again, as if it's just in a repeating cycle. But now what we want to do is look specifically at a type of engine cycle called the Carnot cycle, and really get into the details of what the gas is doing during a Carnot cycle. Okay, so the Carnot cycle was developed by this guy, Sadi Carnot, who was a French mechanical engineer and a physicist who lived in France during the early 1800s. And his primary interest was designing better steam engines. He wanted to make the most efficient steam engine possible. So as part of that, he started thinking about this question of how to build a more efficient engine on a really theoretical level. So when he was only 27 years old in 1824, he described this idealized process, which we now call the Carnot cycle, and he proved through a little bit of math, and we'll show all of this math in this lecture, that the Carnot cycle is the most efficient possible engine cycle. In other words, no matter how you design your engine, no matter what you do, you can never design an engine that is more efficient than this Carnot engine that he came up with. So he is sometimes called the father of thermodynamics because a lot of the work that he did in the early 1800s really paved the way for what we know now, in particular the second law of thermodynamics. So let's now get into what is the Carnot cycle and how do we know it's the most efficient possible engine cycle. Okay, so let's take a close look at the Carnot cycle. Let's see what is this engine cycle that Sadi Carnot proposed way back in the 1800s. And it's basically shown here on this PV diagram. It consists of 4 different steps. And if you follow those 4 steps, you'll come back to where you started, and that will be one full cycle. So how about we start over here at point A? The first thing that happens to the gas is that it expands isothermally at temperature TH. So we'll follow the curve going from point A to point B, and that's an isothermal expansion of the gas, meaning the temperature stays the same, and that temperature is TH. Now, as the gas expands, there's going to be some heat added to it from the outside. So there's an input of heat. We call that QH, if you remember from last time, when the heat flows into the gas. So that's QH. The second thing that happens is the gas expands adiabatically. So as we go from point B to point C, this is an adiabatic expansion. And remember, adiabatic means Q is equal to 0. So while the gas is expanding, there's no heat flowing into or out of it. That's what an adiabatic expansion is. Also, you'll remember that an adiabatic curve is a little bit steeper than an isothermal curve, so that's what's being shown here. So that actually takes us to a different temperature. So as the gas expands, the temperature goes down to TL. So now that's our new temperature after the adiabatic expansion is over. Then the third thing that happens is the gas starts to become compressed. So we go from point C to point D. This is an isothermal compression. So it's isothermal, meaning the temperature is constant. That temperature again is TL. And as we compress the gas isothermally, now some heat is going to flow out of the gas. Okay, so when heat flows out of the gas, we call that QL, or heat exhausted. And that's where that happens in the cycle. This is when the heat gets exhausted. It happens during the isothermal compression. Okay, the last thing that happens then is we follow this curve from point D to point A, which is an adiabatic compression. So again, adiabatic means Q is equal to 0. And if we compress the gas adiabatically, we will end up back here at point A, right where we started. So that's one full cycle. That is one complete Carnot cycle. Those are the different steps that go into it. Okay, so we've seen the Carnot cycle. We know all the different steps that you have to take in the Carnot cycle. And we know what it looks like when you plot it out on a PV diagram for an ideal gas. So what we want to get a better understanding of is how would you actually implement a Carnot cycle? So what would it look like? What sort of things are you doing to the gas to make it undergo the Carnot cycle? I'm going to show you a video that I took from this link here. So if you want to watch the video at home on your own time, you can click this link. It's in the lecture notes. And it basically shows an ideal gas undergoing a Carnot cycle. Okay, so first, you put the gas in contact with a hot reservoir. This is your isothermal expansion, so the gas is expanding isothermally. Now you remove that hot reservoir, so the gas is not exchanging heat with anything, and that's the adiabatic expansion. Now we put it in contact with a cold reservoir. This is the isothermal compression. And then we have the adiabatic compression, where you remove that cold reservoir, and now it's being compressed without any heat exchange. Okay, so isothermal expansion, it's in contact with the hot reservoir. That's what's going on here. And then we remove contact with the hot reservoir, so there's no heat flowing in or out now. It's not in contact with anything, so this is the adiabatic expansion. This is the isothermal compression. Again, it's in contact with the cold reservoir for that. Then you remove the cold reservoir so that it can compress even more, but this time it's not exchanging any heat, so it's adiabatic. So that's what you should have in your mind as far as what the process looks like. But again, the Carnot cycle is an idealization. This is not necessarily something you would want to build. The reason we're thinking about the Carnot cycle in the first place is that it gives us a sense of what the maximum possible efficiency is. That's why we're doing this. Okay, so what we're going to do now is we're going to derive the efficiency of the Carnot cycle. And the way we're going to do that is to remember the definition of efficiency. Epsilon is equal to 1 minus QL over QH. So in order to calculate the efficiency, we just need expressions for QL and QH. Okay, so that's what we're going to be doing. Now remember, QH, that happens during the isothermal process. And QL, the heat exhaust, also happens during another isothermal process. So let's just focus in general on the isothermal process for now. And remember, this means there's no temperature change. So the first thing we can say about an isothermal process is that since delta E internal, change in internal energy is given by N CV delta T, that will be 0, so no internal energy change. And the first law of thermodynamics, as we apply it to an ideal gas, is Q equals W plus delta E internal. So for an isothermal process, what we're going to have is Q equals W. In other words, the heat that flows into the gas is equivalent to the work during an isothermal process. Okay, so Q is equal to W, but W is equal to the integral of P dV. So let's look at the ideal gas law, because this will help us evaluate the integral. PV equals nRT, or we can say P is equal to nRT divided by V. So let's put that into the integral. We have nRT divided by V, that's the pressure, times dV. And since we're isothermal, N is a constant, that's just the number of gas molecules measured in moles. R is a constant, and of course T, temperature, is constant. So we can pull all of those out, and we're just left with dV divided by V, going from V initial to V final, whatever those initial and final volumes happen to be. So when you integrate 1 over V, you get the natural log of V, and we're taking this from V initial to V final. So we have nRT times the natural log of V final, that's our top limit which we plug in, minus the natural log of V initial, that's the bottom limit that we plug in. And of course we can combine these into the same natural log function by dividing V final divided by V initial inside the natural log. Okay, so that's generally the expression for the heat transferred to the gas during an isothermal process. So if we specifically consider the process that takes us from A to B, that's this one over here, process 1, then the heat added to the gas during that process is going to be N times R, and specifically the temperature is TH. So let's label this TH. And then I have the natural log of the final volume, which is VB, divided by VA. And so we can call this QH because, again, that's the heat that's input to the gas during that process. Now, we care about absolute values here, so we have to be a bit careful. QH is positive. Okay, the heat's flowing into the gas during that process. So the absolute value is just the expression we came up with, nRT, TH that is, times ln VB over VA. So there's QH, and we're going to use that in our expression for efficiency. Next, if we consider the process from C to D, that's when we have QL. That's when the heat is exhausted. So we have N times R. The temperature is now TL. And then we have the natural log of the final volume, which is VD, divided by the initial volume, which is VC for that process. Okay? Okay, but this is going to be something negative because heat is flowing out of the gas. Okay, so what we want to do is come up with an expression for the absolute value of that. So the absolute value of QL would just be minus nRTL times natural log VD over VC. So we can take that a step further because if you remember, we basically have a factor of -1 out front. That's the way you can think about that. And I can put that factor of -1 into the natural log as a power. So this would be VD over VC to the -1 power, in other words, which would be N times R times TL times natural log VC over VD. So just flip the order of terms to get the absolute value. And so here's what we have for the efficiency. Remember, it's 1 minus QL divided by QH, absolute values. So I have 1 minus, okay, QL was N times R times TL times the natural log of VC divided by VD. And then QH was N times R times TH times the natural log of VB divided by VA. Okay, so right away we can cancel out N and R. And we can even go a little bit further with this. So far in our derivation, we've only considered the isothermal processes, the ones that take us from A to B, and from C to D. Let's now think about the adiabatic processes. Okay, so now we'll consider the adiabatic expansion, which on our diagram takes us from point B to point C. So process number 2 over here is what we're looking at now. And I want you to remember that for an adiabatic process, we have a certain set of relationships that we derived back in chapter 19 between the pressure and the temperature and the volume during an adiabatic process. And one of those relationships was T times V to the gamma minus 1 is constant. So we're going to use that and apply it to the process, again, that takes us from B to C. Okay, from the diagram, the temperature at point B is TH. Okay, we're at temperature TH, but then once we get to point C, the temperature is TL. And then the volumes, we're going to call them VB and VC. So here's how we'll use that. We'll have, okay, TH times VB to the gamma minus 1 is equal to TL times VC to the gamma minus 1. Okay, so that's what we have for that process. Now we'll consider the adiabatic compression. And that's the process that takes us from D to A. And again, we'll use that same relationship. So at point D, down here on the diagram, my temperature is TL. And then once I go to point A, my temperature is TH. Okay, so the relationship will say TL times VD to the gamma minus 1 is equal to TH times VA to the gamma minus 1. Okay, so we have these two adiabatic relationships. Let's now put them together. Okay, so on the left side of my equation, I'm going to write TH VB to the gamma minus 1 divided by TH VA to the gamma minus 1. What does that equal to? Well, on the top, I have TH times VB to the gamma minus 1. I know that's equal to TL times VC to the gamma minus 1. So that goes on top. On the bottom, I have TH times VA to the gamma minus 1. I know that's equivalent to TL times VD to the gamma minus 1. In other words, we're sort of just taking these two equations and dividing one by the other. And that simplifies things because TH goes away, TL goes away. And what we have is VB divided by VA to the gamma minus 1 is equal to VC divided by VD to the gamma minus 1. So that just means that, VB over VA is equal to VC over VD, which guess what? Means natural log VB over VA is equal to natural log VC over VD. Now, the reason we did all that is because if we go back to our expression for the efficiency, on top we have natural log VC over VD. On the bottom we have natural log VB over VA, but we just showed those are the same thing, so you can cancel it out. Therefore, all we're left with for our efficiency is 1 minus TL over TH, and that is the efficiency of the Carnot cycle. 1 minus TL divided by TH. The only thing that matters in the Carnot cycle as far as the efficiency goes is the temperature of the hot region where you're taking in heat and the temperature of the cold region where you're exhausting the heat. Okay, so that's how you derive the Carnot efficiency. That's where it comes from. And if we go back to the heat engine schematic that we developed in the last video, we remember that we have a hot reservoir, temperature is TH, a cold reservoir, temperature is TL, and then we have our working substance, which in the case of the heat engine is going to be an ideal gas of some kind. We have QH, that's the heat that flows in from the hot reservoir into the gas at some point during the cycle. We have QL, that's the heat that's exhausted into the cold reservoir at temperature TL. And then, of course, we have some work being done. So the efficiency of the Carnot engine only depends on those two temperatures of the hot and the cold reservoir. TH and TL are the only things that matter as far as efficiency goes. The actual details of how you design the engine, what kind of gas you use, or anything like that simply don't matter as far as the efficiency is concerned. So the formula we derived is epsilon Carnot, efficiency of the Carnot engine, is 1 minus TL over TH. Now, in order for this formula to work, TL and TH must be absolute temperatures, so measured in the Kelvin scale. And the reason for that is, as we derived this formula, we used the ideal gas law. And whenever we use the ideal gas law, we're assuming absolute temperatures. So that carries over into the final result. And finally, the Carnot efficiency is really important because it truly represents the maximum possible efficiency of any engine that operates between these two temperatures, TL and TH. And notice how this efficiency is never going to be equal to 1. It's always going to be less than 1. How much less than 1 depends on the temperatures TL and TH, but epsilon equal to 1 is not possible. So the next thing we're going to do is prove why this efficiency is the absolute best you can do. You can't do better than the Carnot efficiency. Okay, so the goal here is to prove that you can't have an efficiency that's better than the Carnot efficiency. And the way we're going to do this is by contradiction. So proof by contradiction. That means we're going to assume that you can have an engine that's more efficient than Carnot. We're going to assume that that is possible. And then we're going to see that leads us to a nonsense conclusion. It leads us to an impossible conclusion, which means what we assumed is false. You can't have an engine more efficient than the Carnot efficiency. So this is how we're going to set everything up. We suppose we have two engines. Okay. You have a Carnot engine. That's going to be number 2. And then we have an engine that's better than Carnot. So that will be engine number 1. So what we're saying here is the efficiency of engine number 1 is better than the efficiency of engine number 2. Okay, so the nice thing about the Carnot cycle is that it's reversible. So if we have a Carnot engine, we can run it in reverse as a refrigerator. So here, the Carnot engine, that's the one we're labeling number 2, can be run in reverse as a refrigerator. Okay. So here's what we're going to do. We're going to have engine number 1. This is the one that's supposedly better than Carnot. We'll power number 2 run in reverse as a refrigerator. So here, let's draw a picture of what that looks like. So first, we have a hot reservoir. The temperature is TH. Then we have a cold reservoir down here. Temperature is TL. Okay, so number 1 is this engine that's supposedly better than Carnot. If we want to show how it's operating, well, some heat has to flow into it. Let's call that QH1. And it's going to do some work. Let's call that W1. And then it's going to give off some exhaust heat into the cold reservoir. Let's call that QL1. Then let's draw the second one. This is the Carnot engine, which we're running in reverse as a refrigerator. So what's happening here is some work is put in to this one, W2, let's call it. And then we have QL2 coming from the cold reservoir into the refrigerator. And then we have QH2 going into the hot reservoir like this, okay? So that's how we show engine number 1 powering refrigerator number 2, which again is just a Carnot engine run in reverse, okay? So since number 1 is powering number 2, we have that work 1, at least in terms of magnitude, is equal to work 2, because the work output by engine number 1 is the work that's input to this refrigerator. So what we can then do is say, what is W net? What is the net work done by 1 and 2 together? Well, that's just going to be W1 is positive, okay, because the gas of the engine of number 1 is doing positive work. W2 is going to be negative. And since they have the same size, there's 0 overall work being done, okay? So the system, in other words, which is 1 and 2 together, does 0 net work. Okay. The next thing we can do is bring in the idea of efficiency. Remember, efficiency in general is the work divided by QH. But we can solve for QH, and that would be the work divided by the efficiency. So here's the idea. Since efficiency 1 is bigger than efficiency 2, that's what we're assuming, right? If the work is the same and the efficiency is bigger, that means QH is going to be smaller. Okay, in other words, QH1 is going to be less than QH2. Because again, the same amount of work, but epsilon is bigger for 1, so that's what we get. Okay, so next, let's calculate QH net. So in other words, what is the total heat flow going into the hot reservoir between these two objects? Okay, so we have QH1 is positive because it's flowing into that gas. QH2 is negative because it's flowing out of that gas over there. And again, since QH1 is, since QH2 is bigger than QH1, this is going to give us something negative, okay? Because you have one number minus another, where this one is bigger, that gives you something negative. And this is saying there is a net heat flow out of the system. Again, that's just 1 and 2 together, into the hot reservoir. Okay, that's what we have. Okay, next. The first law of thermodynamics applied to an engine cycle says QH is equal to W plus QL. Therefore, QL is equal to QH minus W. So here's the thing. We established that W is the same for these two, but QH is bigger for the second one. So if you look at this formula, if QH is bigger, but W is the same, then QL is also going to be bigger for number 2. So QL2 is going to be bigger than QL1. Okay? So guess what we're going to do next? We're going to look at the net heat flow. QL net. So if we go to the diagram, for number 2, there's heat flowing into the gas from the low temperature region. So that's going to be a positive heat flow, QL2. But for number 1, heat is flowing out of the gas into the low temperature region. So that would be a negative heat flow, QL1. So we have QL2 minus QL1 to get the net heat flow. But remember, we just said that QL2 is bigger. So that means this is something positive, which means there is a net heat flow into the system. Again, that's 1 and 2 together from the cold reservoir. Okay. So what does this look like when we put it all together? So we have TH, the hot reservoir. Let's just draw 1 and 2 together as a single system like this. And then we'll have the low temperature region down here, TL. So what have we found? Well, the net work is equal to 0. There's a net heat flow, remember, out of the system into the hot reservoir. We found this up here. So out of the system into the hot reservoir is QH net. And then over here we found there's a net heat flow into the system from the cold reservoir. So that's shown by this arrow, QL net. Okay, there's something very wrong with that picture. Heat doesn't flow from cold to hot all on its own. And that's what this picture is showing us. We're just seeing that heat is flowing out of the low temperature region and into the high temperature region without anything else going on. That's not possible. This actually violates the second law of thermodynamics, as we're going to see. So, what did we assume at the beginning? What we assumed at the beginning, that you have this engine that's better than Carnot, that was wrong. You can't have an engine more efficient than Carnot. That is not possible. We just proved that by contradiction. And so let's do an example where we take this formula for the Carnot efficiency, and we know it's the maximum possible efficiency, and we can put that to use in a calculation. So in an internal combustion engine found in a typical car, the fuel is ignited to a temperature of about 1500 degrees Celsius. Let's say that the engine exhaust goes into the surrounding air, which has a temperature of 25 degrees Celsius. So given those two temperatures, what is the maximum theoretically possible efficiency of such an engine? And then for reference, let's just take note that the best efficiency that has been achieved is somewhere around 40%. As we're going to find, that's way less than the maximum possible theoretical efficiency. So why is it that the maximum possible is so much less than what's actually been built? Let's think about that. Okay, so TH is the high temperature. This is the temperature at which the fuel is ignited. It's going to be 1500 degrees Celsius, but we want to get this in Kelvin, so add 273. And you get 1773 K. For TL, same deal. This is the low temperature at which the heat is exhausted, and that's going to be 25 plus 273 to get that in Kelvin, 298 Kelvin. So we know the maximum possible efficiency is the Carnot efficiency. And the Carnot efficiency is given by 1 minus TL divided by TH. Okay, so we have 1 minus 298K divided by 1773K, which works out to about 0.83 or about 83%. So that's the best you could possibly do, roughly speaking, with an internal combustion engine. But in reality, the best we can really design is somewhere around 40%. So in other words, there's a lot of room to improve. If you're a mechanical engineer or an automotive engineer, there's a lot of room to design a more efficient car engine, okay? And so why is it that we're so far away from the best possible efficiency? Well, here's what's going on in a real engine. Okay, you've got things like friction. That is a big factor in why the engine can't get to the best efficiency. Here's another thing. Imperfect heat transfer. Okay, so when you ignite the fuel, not all of that heat is going into expanding the gas. Some of it just sort of leaks out into the environment. There's going to be energy used by other equipment in the engine itself, like oil pumps, for instance. So to move oil around within the engine, that wastes some of the energy. There are a bunch of other things we could say, but there are a whole lot of reasons why the best possible is 83% around there, and the best we've ever been able to achieve is about 40. And there's a lot of room for improvement as an engineer to make a more efficient engine. Okay, so here's one for you to try out. We have a salesman that's claiming that the heat engine he's trying to sell you has an efficiency of 65%, and it operates between two temperatures. TL is 200K and TH is 500K. Should you trust the salesman? So pause the video, see if you can work this out, and then come back to it and we'll go over the result. Okay, so what we want to do here is compare the efficiency that's being claimed by the salesman, which is 65%, or as a fraction, 0.65. And we want to compare that to the Carnot efficiency. Because on its face, 65% may seem reasonable. He's not claiming 100% efficiency. But remember, you can't do better than Carnot, which is 1 minus TL divided by TH, which in this case would be 1 minus 200K over 500K, which would only work out to 0.6. The salesman is claiming better than Carnot efficiency. So here, salesman is claiming better than Carnot efficiency. And you automatically know that's bullshit, that's wrong, that's a lie. So do not trust the salesman. Okay, that's physically impossible, what he's claiming. Okay, so now let's take a look at the Carnot refrigerator. So a Carnot refrigerator operates on the exact same cycle as a Carnot engine. We already know what that looks like on a PV diagram, except everything is run in reverse. Every part of the cycle just goes in the reverse direction. So remember, for the engine, we started at point A, then point B, then point C, then point D, and then back to point A. Now we're going to run it the other way. So if we start at point A, we have an adiabatic expansion of the gas that takes us to point D, followed by an isothermal expansion, which takes us to point C, followed by an adiabatic compression, takes us to point B, and then an isothermal compression takes us back to point A. So that's the cycle. It's the same exact cycle as before, but everything is in reverse. And just like the Carnot engine, the Carnot refrigerator has the best possible coefficient of performance. Okay, so the Carnot engine has the best possible efficiency. The Carnot refrigerator has the best possible coefficient of performance. So now what we're going to do is derive the formula for the Carnot coefficient of performance. Okay, so we'll start by writing down the definition of the coefficient of performance for a refrigerator. And remember, you can think of this as what you get out divided by what you put in. What we want a refrigerator to do is to remove heat from the low temperature region, which is QL. And what you have to put in is some amount of work. So W, the ratio of QL over W is the coefficient of performance. But this can be written as QL divided by QH minus QL. So to get the coefficient of performance for a refrigerator, all we need to know is QL and QH. Now, we've already worked with the Carnot cycle before, so a lot of results we already have from the previous derivation. So from the derivation of the Carnot efficiency, we have, okay, so one thing we know is that VB divided by VA is equal to VC divided by VD. So those ratios of volumes were worked out in the previous derivation. We also know that for an isothermal process, Q is equal to N times R times T times natural log of V final over V initial. So again, this is for isothermal. And that's what we found in the previous derivation. So now what we'll do is use the formula for Q, and we'll apply it to the process D to C. So the gas expands isothermally from D to C, and that's when we have QL. Okay, that's when the heat is transferred at the low temperature. And so QL is equal to N times R times TL, specifically that's the temperature. And then we have the natural log of the final volume, which is VC, over the initial volume, which is VD. And by the way, this is going to be positive because heat is flowing into the gas. So that's also the absolute value of QL. Okay, we also need to look at the process that takes us from B to A. And the process from B to A is another isothermal process. So we know that Q is given by N times R times T divided by natural log V final over V initial. In this case, we're talking about QH. The temperature is TH. And we have the natural log of the final volume, which is VA, divided by the initial volume, which is VB. But here's the thing. QH is negative because heat's flowing out of the gas. And volume B is bigger than volume A. So you're taking the natural log of something less than 1. It gives you a negative number. So QH is negative. If we want the absolute value of QH, then we have to undo that negative sign. So this will be negative nRTH times the natural log of VA divided by VB. And remember that trick I showed you in the last derivation? I can take this negative sign and put it as a power inside of the natural log. So this would be nRTH natural log VA over VB to the minus 1. That's just like taking the inverse or flipping the fraction. We have nRTH natural log of VB divided by VA. Okay, so that's the absolute value of QH. Now, we can plug all of that in to the expression for the coefficient of performance. So COP for the Carnot refrigerator would be, we have QL on top. So that's N times R times TL times natural log VC over VD divided by QH minus QL, nRTH natural log VB over VA minus nRTL natural log VC over VD. So just plugging in the Q expressions that we derived. So first, nR goes away. And then also, because we know the ratio of volumes that appear in the natural log here are the same, in other words, VC over VD is the same as VB divided by VA, that cancels as well. And then we're left with TL over TH minus TL. That's the Carnot coefficient of performance, and it represents the best possible coefficient of performance for any refrigerator that you could design. Okay, so the coefficient of performance for a Carnot refrigerator that we derived is TL divided by TH minus TL. And again, think of that as the maximum possible coefficient of performance. That's something you can't do better than. And this is not ever going to equal infinity, by the way. So a perfect refrigerator where you don't put any work in, that gives you an infinite coefficient of performance, that's not possible. The highest you can get is this value here. The last thing to say about this is the temperatures must be given in Kelvin for this formula to work. So just like before, assume absolute temperatures in units of Kelvin when you use this formula. Okay, so let's get a little bit of practice using that result. Suppose that on a hot day, the temperature outside is 41 degrees Celsius. You are using an AC unit to cool your house to a temperature of 21 degrees Celsius. What is the maximum theoretically possible coefficient of performance for this AC unit? So in other words, calculate the Carnot coefficient of performance. And for comparison, a good coefficient of performance for a real AC unit would be something around 4, okay? And if you want more information about how an actual AC unit or an actual refrigerator is designed, to get more into those details, I left a link here, and you can check that out. It's a very good explanation. So click on that if you're interested. But anyway, pause the video, see if you can work this problem out, and we'll go through it together afterwards. Okay, so I thought we'd start this one by drawing a schematic of an AC and air conditioning unit. So the kind of simplified picture is we have a hot reservoir that has temperature TH, and we have a cold reservoir that has temperature TL. And then we have our working substance. That's our gas. And so what you have to do is put some work in. There's going to be some sort of motor inside of the AC unit. You have to do some work. That's W. You're also going to be moving some heat out of the cold region into the working substance, and that's what we call QL. You're also going to be dumping some heat into the hot region out of the working substance, out of the gas, and that's going to be QH. So by the way, the goal of an AC unit is to remove heat from the cold region. So the inside of your house, that's the low temperature region. You're trying to take heat out of your house, remove heat from your house, that's QL. The outside is the hot region. That's what has temperature TH. Okay? So the best possible coefficient of performance is, of course, the Carnot coefficient of performance, so COP Carnot. And we just derived that that was equal to TL divided by TH minus TL. We have to get these temperatures in Kelvin because we have them in degrees Celsius right now. So for the low temperature TL, that's 21 degrees Celsius. That's the temperature inside the house. Add that to 273 to give you 294 Kelvin. For TH, it's the high temperature. It's the temperature outside of the house. It's going to be 41 degrees Celsius plus 273 equals 314 Kelvin. So the best you can do in terms of a coefficient of performance is you have 294 K divided by 314 K minus 294 K, which is 14.7. That's the best you could do. Now, so that's the maximum theoretically possible coefficient of performance. And if you compare that to a real AC unit, it's going to be something more like 4. So again, this is showing us there's a lot of room to improve our existing AC units and make them better and more efficient because we're not getting anywhere close to the maximum possible coefficient of performance. Okay, so next we'll talk about another type of engine cycle. It's called the Otto cycle. And this is a pretty good approximation of what's going on inside of a car's engine. So it describes pretty well what's going on in an internal combustion engine. So this is what an Otto cycle looks like when we plot it out on a PV diagram. So we have 4 different processes. And if we start at some point on the diagram and we follow those 4 processes, we end up right back where we started. So it's an engine cycle. It can just repeat itself over and over again. And the first part of the cycle, if we start here at point A, is that the gas expands adiabatically from point A to point B. So we start at a volume that I'm going to call V min, and we end up at a volume I'm going to call V max. And again, an adiabatic expansion means there's no heat flowing into or out of the gas, so Q is equal to 0 during that process. The next thing that happens is we're at point B, and the gas is going to be cooled isochorically, so no volume change, as we move to point C. So since the gas is cooling off, it's giving off heat to the environment. Heat is flowing out of the gas. That's QL, that's the exhaust heat. The next thing that happens is that we have an adiabatic compression from Vmax back to Vmin. And again, adiabatic means there's no heat flowing in or out of the gas during this step of the process. The last thing that happens is we heat the gas up isochorically. So again, no volume change here from point D to point A. So while that's happening, there's heat flowing into the gas now. There's an input of heat, which we call QH. That's where it happens right here. So that's the Otto cycle. What we're going to do now is derive a formula for the efficiency of the Otto cycle. Okay, so this is going to be a derivation of the Otto efficiency. And remember, in general, the efficiency of an engine is given by 1 minus QL over QH. So we just need expressions for QL and QH, and then we can derive the efficiency from that. So I'm going to start by thinking about an isochoric process in general. This means constant volume, delta V is equal to 0, no volume change. And since we have two of those in the cycle, we have step number 2 and step number 4 are isochoric. Let's do a little bit of work on that. So during an isochoric process, we can calculate the work. Remember, that's the integral P dV. Or we can think of that as the area under the curve on a PV diagram. But of course, if the volume is not changing, that work is equal to 0. There is no area under the curve if you just have a vertical line at constant volume. The next thing we can do is look at the first law for ideal gases. And remember, this says Q is equal to W plus delta E internal. Well, if work is equal to 0, then Q is just equal to delta E internal. And remember that the change in internal energy is given by N times CV times delta T. Okay? So in the case of, let's say we want to do QH. Okay? Let's do that. So if we consider the process that takes us from D to A, that's where QH is coming into the gas. Well, that's going to be given by N times CV times delta T. So that's T final minus T initial. The final temperature would be TA. The initial would be TD. And this is going to be something positive because the temperature up here at point A is going to be greater than the temperature here at point D. So the heat is positive, in other words. So that's just equal to the absolute value QH because it's already positive. If we go from B to C, however, we can use the same formula for Q. Again, this is another constant volume process, so we already know the formula for Q. It's going to be N CV delta T. This time, our final temperature is TC minus our initial temperature, TB, and this is what we would call QL. Now, the temperature down here at point C is less than the temperature up here at point B. In other words, the gas is cooling off, and the heat is flowing out of the gas, meaning QL is something negative. So if I want the absolute value of QL, then that would be negative NCV times TC minus TB, which is the same as saying NCV times TB minus TC. Just flip the order of terms around, in other words, to make it positive. Okay, so then our efficiency is 1 minus, remember we have QL divided by QH. QL is NCV times TB minus TC. QH is NCV times TA minus TD. Okay, so N times CV cancels out. Get rid of that. The next thing I want to think about is the adiabatic processes. We haven't looked at that yet. So one thing we know about an adiabatic process is that T times V to the gamma minus 1 is constant during an adiabatic process. So we have two of those to think about. That would be the process that takes us from A to B and the process that takes us from C to D. Those are both adiabatic, so we can use this relationship for both of those. Okay, let's say we use it for the process that takes us from A to B. Okay, so we'll have the temperature at A times the volume at that point, but we're calling that V min. Okay, that's just how we're labeling that volume, V min. And then I'll have gamma minus 1 here. And that will equal the same thing at point B, which would be TB times the volume, which is now V max, to the gamma minus 1. Okay, let's do the same thing for the other adiabatic process. Again, that's the one that takes us from C to D. That one gives us TC times the volume at that point, which is V max, to the gamma minus 1. That equals TD times the volume, which is V min, to the gamma minus 1. Okay, so we have these two adiabatic relationships. Here's what we can do with them. So I'm just going to write on one side of the equation TB times V max to the gamma minus 1 minus TC times V max to the gamma minus 1. So I'm just looking at these two terms in the equation that have V max next to them, and I'm just putting them together. I'm subtracting one from the other. Well, I automatically know what that equals because the first term, TB times V max to the gamma minus 1, is equal to TA times V min to the gamma minus 1. And if I'm subtracting from that TC times V max to the gamma minus 1, I know that's equal to VD times V min to the gamma minus 1. So basically, using the two equations above, we can sort of subtract one from the other, essentially is what we're doing here. And we construct this equation. So notice we have TB minus TC multiplying V max to the gamma minus 1 equals TA minus TD multiplying V min to the gamma minus 1. If we rearrange this a little bit, let's divide through by TA minus TD. So we have TB minus TC divided by TA minus TD. Let's also divide through by V max to the gamma minus 1. So on the other side, we'll have V min to the gamma minus 1 over V max to the gamma minus 1, which I can write as V min over V max to the gamma minus 1. By the way, if you're into cars, you may know what this is. This is called the compression ratio. So the ratio of the minimum volume to the maximum volume is the compression ratio. Sometimes we call that R. So this would be R to the gamma minus 1. Okay, the point of all that is to say, in the efficiency formula, we have this exact fraction. We have TB minus TC over TA minus TD, and we can replace that with V min over V max to the gamma minus 1. So that's what I'm doing in the efficiency formula. So the Otto efficiency, the efficiency of this cycle, is equal to 1 minus V min over V max to the gamma minus 1, which is 1 minus R to the gamma minus 1 if we call this the compression ratio. Okay, so that's the derivation. Okay, so now let's take a closer look at the formula we derived for the efficiency of the Otto cycle. So basically, this efficiency depends on two factors. One of those factors is R. That's what we call the compression ratio of the piston, and it's defined as V min divided by V max. And it also depends on gamma. So remember what gamma is from the previous chapter. Gamma has to do with the number of degrees of freedom of your gas molecules. So it's actually going to make a difference what type of gas you're using as far as the Otto cycle efficiency is concerned. Okay, so the actual working substance and the details of that will matter as far as the Otto cycle is concerned. So with that said, let's do a sample calculation. Suppose you have an ideal Otto engine with a compression ratio of 0.1. So V min divided by V max in this case will be 0.1. Which working substance will make the engine more efficient? So molecular oxygen, that's O2, or helium, that's a monatomic gas, He. So to answer this question, think about the number of degrees of freedom each type of gas particle has. This is not a super realistic question because these don't really make good fuels, but purely in terms of efficiency, which one gives a bigger value of E? That's what I want to know. Okay, so try to work this out, see what you come up with, and we'll go through it together. Okay, so we'll start with this. The efficiency of the Otto engine is 1 minus R to the gamma minus 1. We derived that just a second ago. And in this problem, we're going to assume a compression ratio of 0.1. Now, gamma, the power that we see in this equation, is Cp divided by Cv. That's the definition of gamma. So it's the ratio of the specific heats. But we saw that we can write this as 1 plus 2 over F. So that was all found in chapter 19. So F here represents the number of degrees of freedom of the molecules. So in other words, if we have different types of gas molecules being used, we'll get different results as far as the efficiency goes. So we'll start with helium. Helium is monatomic. So we have a monatomic gas. We learned in chapter 19 that we'll have 3 degrees of freedom. F is equal to 3 for any monatomic gas. The other one was O2. Yeah, O2. So think of that as 2 oxygen molecules connected by a bond. This is a diatomic gas. And a diatomic gas has more degrees of freedom. Okay, so it depends on some specifics, but let's just remember what types of degrees of freedom might we have. We might have translation, rotation, and vibration. So at normal temperatures, unless you're really, really cold, rotational degrees of freedom are going to be there. Translational will always be there. But vibrational degrees of freedom are typically frozen out unless the temperature is ridiculously high, like several thousand Kelvin. So we can assume those are frozen out. And how many of each type do we have? Well, we have 3 translational and 2 rotational and 2 vibrational. But again, the ones that are active is going to be 3 plus 2, which is 5. Okay? So it's reasonable to assume about 5 degrees of freedom here. So the efficiency we would get with helium is 1 minus the compression ratio of 0.1. And then we have gamma minus 1. So here, if gamma is 1 plus 2 over F, gamma minus 1 is just 2 over F. So the power is 2 divided by 3. And that gives 0.78. Now, if we were to use oxygen, O2, then we would have 1 minus 0.1. And then we have 2 over F. that would be 2 over 5, which would come out to 0.6. So again, if we're strictly speaking about efficiency, it would be helium that wins out. But again, you wouldn't really want to use that as a fuel because helium doesn't react well, it doesn't combust. So strictly speaking, this only wins out in terms of efficiency. Okay, so the last thing I want to go over is what a real internal combustion engine cycle looks like. So this is what would actually be happening inside of the engine in your car. The Otto cycle is a rough approximation of this, but the reality is a little bit messier. Okay, so what I want to show you is what a real engine cycle looks like. So there's sort of two things I want to think about. What is the basic makeup of one of your cylinders in your engine? What are the different parts? What do they all do? And then how does the engine cycle look when we plot it on a PV diagram? And we'll want to kind of connect those two. So we'll start with this picture of the different components. The first thing to note is that we have a piston, and the piston can move back and forth. And it's connected to a crankshaft, and basically what that does is it converts the back and forth linear motion of the piston into rotational motion, and that can drive the motion of your wheels. Okay, we have a couple different valves at this end. This is called your intake valve. So when the intake valve opens up, it can let some fuel go into the piston. We have the exhaust valve, so when the fuel is used up, it can exit the piston. We also have a spark plug. So the spark plug is there so that you can ignite the fuel. And when you do that, it releases a bunch of heat. That heat is what drives the engine, okay? So let's do this on the PV diagram. We'll start here. So the first thing that we'll see is the intake valve opening up. Okay, so you're gonna open up this valve and allow some fuel to come into the piston. Then we're gonna move along this line. So notice how the pressure is pretty low and the volume is increasing. So what's happening? The piston is moving back this way, increasing the volume, but since the intake valve is open and air can just flow into here and fuel can just flow in, the pressure is more or less constant throughout that. Okay, so as we move along that line I just showed you, this is called intake, where a mixture of air and fuel is drawn into the cylinder, okay? The next thing that happens is we move along this curve. So at this point, the intake valve closes. So it's open for a while so we can get some fuel in there, but then at some point it has to close. The reason we close it up is now we're gonna compress the gas, so the volume is gonna decrease. And if that valve is closed, as we compress the gas, the pressure is gonna go up, okay? So the pressure keeps going up and up. We call that the compression phase. And then at the end of our compression phase, when the piston is back over here and the volume is very small and the gas is under a lot of pressure, the spark plug ignites the fuel. Okay, so that's where the spark plug goes off and ignites the fuel. Okay, this next part is called the power stroke because the spark plug ignites the fuel right here when the piston is at the top. That fuel that just ignited is going to drive the piston back down. It's going to push it way back down where the volume starts increasing again and the pressure starts dropping again. That's what we call the power. Okay, at the end of that part of the cycle, your exhaust valve opens up, and basically that allows you to let this fuel that you've used up out of the cylinder. And that's called the exhaust phase. The piston goes back, pushes back towards the valve and pushes that used up fuel out of the exhaust valve. Okay, and then we're back to where we started. This happens all over again. It keeps happening over and over again, many, many times per minute, and that's what drives the motion of your car fundamentally. So if we take a look at an animation of that, here's what it looks like. So we're drawing the fuel in, spark plug goes off, ignites the fuel, exhausted, and then the fuel comes back in, spark plug ignites the fuel, that used up fuel gets exhausted. This is the cycle that keeps happening inside your car's engine. So that's going to be it for today. We'll continue on with this lecture in the next video where we'll begin to talk about entropy. But until then, take care, be safe out there. I'll see you in the next one.